right, everybody. I am actually going to be going over the FRQs together with you guys on the videos to kind of show you a couple different ways that you can answer some of the questions. One of the limitations, I think, with the answer keys that I post for you is that they don't leave any kind of wiggle room for explanation, or if you get stuck, they maybe don't really explain what's going on. So I'm hoping to do that with these. So I'm going to work with these, work through these FRQs with you, and if you have any questions, let me know with the meet or by email. Excuse me. All right, so this is Unit 1, FRQ 2008, question number 3. This is a full-length, big, beefy FRQ. This is probably the size and style that you could probably expect to see on the exam in terms of its quantity of questions. So for A, it says to write the ground state electron configuration of the Fe2 plus ion. So Fe2 plus ground state electron configuration means it's the lowest energy state possible. When we think about our normal electron configuration, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6. So that's what we normally have for iron. But in the case of Fe2+, we are losing 2 electrons. So 2 of these are going away. And I know that your natural inclination is to say, okay, well, these things are disappearing, so I must have to lose them from the D shell. But there's actually a unique thing that happens with elements that are in that period on the periodic table. Because the electrons, sorry, I gotta grab my table. Because the electrons in the 4s and the 3d shells are actually so close together, as soon as you start to put electrons into the 3d shell, it actually drops lower in energy and closer to the nucleus than the 4s shell does. So the true electron configuration for the ion of this isn't losing 2 electrons from the D shell, it's actually losing these 4s electrons. And all of the elements that are in that 3D shell do the same thing. So the correct electron configuration loses these 4s, and so it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. But if you aren't interested in writing that, the abbreviated electron configuration is going to be argon 3d6. Okay, so that's question 1A. On the key, it's worth 1 point because of the electron configuration. Okay, B. The radii of the ions are given in the table above. Using principles of atomic structure, explain why the radius of the Fe2 plus ion is larger than the radius of the Fe3 plus ion. So if you look in the data table that's given to you, they refer to the size of the radius. PM is picometers, 92 picometers for Fe2 plus, and 79 picometers for Fe3 plus. In the case of B, the radius of Fe3 plus is going to be smaller and it's smaller because of the proton to electron ratio. Okay, so because of its proton to electron ratio, it ends up being smaller. Now, that is not a sufficient answer. You actually have to explain. So what I'm going to say is Fe3 plus and Fe2 plus have the same number of protons, but Fe3 plus has fewer electrons, 1 fewer. Okay, so there's 1 fewer electron. What I'll say then next is that 1 fewer electron allows the nucleus to pull those protons, or pull those electrons closer. Okay, so what I've mentioned is the ratio of protons to electrons, and how if there are more protons than electrons, the bigger that ratio is, the more that they can pull them in. In the answer key, it talked about them having greater electron repulsions, but in this case, my answer would work just as well as the answer key, because I'm kind of talking about the same thing, just approaching it from a nucleus forward thing versus an electron repulsion argument. So both of those I think would be okay. And that's why we're kind of going over these, is because we can get different things happening. All right. So for C, it says Fe3 plus ions interact more strongly with water molecules in aqueous solution than Fe2 plus ions do. Give one reason for this stronger interaction and justify your answer using Coulomb's law. So Coulomb's law, they give you the information about what you got to think about already. So in a Coulomb's law argument, there are two things. There is either, if you remember, a size argument or a charge argument, and you can pick either of them to talk about this. So you can say that the interaction is happening because the Fe3 plus has a higher charge, so it has a stronger interaction. So that is one thing you could talk about. The other thing that you could talk about is that you could talk about Fe3 plus has a smaller size. And then it would be identical to this part here. So either of those would be fine. It's kind of up to you how you want to approach that. But when they talk about Coulomb's law, it is either going to be a charge argument or a size argument, and it's one or the other. It says that you do not necessarily need to reference Coulomb's law, the Q1 times Q2 over R squared. So it just either has to be a size or a charge argument. The idea of Coulomb's law, not actually talking about Coulomb's law. Okay. The next question is D. A student obtains a solution that contains an unknown concentration of Fe2 plus. To determine the concentration of Fe2 plus in solution, they titrate, titration, fun times, a sample with MnO4, which is the permanganate polyatomic ion, which converts Fe2 plus to Fe3 plus as represented below by the following equation. So they give you the equation here, and then for D, they ask you to write a balanced equation for the half reaction for the oxidation of Fe2 plus to Fe3 plus. So we know that's going to be Fe2 plus to Fe3 plus. And the trick with this is that they're telling you that it's an oxidation. But if you don't remember what an oxidation is, you can think about where the charges have to go in an oxidation reduction. Electrons are moving in this. So if I add an electron to my reactant side, I'm going to end up with a +1 charge. If I add my electron to the product side, I am going to end up with a +2 charge, and that's what I need to balance these two things out. This is probably honestly the only type of oxidation reduction reaction question they could ask you on the test. And so this is what you need to be prepared for. Okay, so that is D. All right, moving on to part E. It says a student takes titrates a 10 milliliter sample of Fe2 plus solution. Calculate the concentration of the Fe in solution if it takes 17.4 milliliters of added KMNO4 to reach the equivalence point of the titration. Now, in a titration, you can approach this from one direction or the other. You can use this as a stoichiometry problem, or you can use it as a M1V1 over N1 problem, and it's kind of up to you how you want to do it. Titrations, I think, are easier to remember as M1V1 over N1, so that's what I am going to do. The answer key shows you what this looks like as stoichiometry, so if you prefer the stoichiometry, you can do it that way. But I like to do this because I think it's a little bit faster, and they take both of them. So when you think about a titration and you're trying to figure it out, you kind of want to think about it. Oh, I'm sorry, it's not Fe3 plus, it's Fe2 plus. So what you want to do when you think about these is you want to think about them as two sides of this, essentially. It is going to be, let me see if I can zoom in a little bit more. It is going to be the titrant, and the analyte. So they are analyzing the Fe2 plus side. So what I'm going to do is I'm going to collect all the information for the Fe2 plus. So I am looking for that concentration. That's the M1 part of this. So I'm looking for the concentration of Fe2 plus. That's the stuff in the brackets. And it tells me in the problems that my sample of iron is 10 milliliters. So that is going in my V1. Now, you cannot just leave it like this. You have to do a little bit more. You have to include the mole ratio numbers. And that goes back to your problem from the previous part. It tells you that there is a coefficient of 5 in front of the Fe. So I'm going to divide that by 5 moles. Okay, now it's technically, it's 5 moles of iron, but you can just leave it since this is the iron side. Now I am titrating it with the potassium permanganate. When I titrate it with the potassium permanganate, if I look at the information that's given to me in the problem, it tells me that the molarity of the potassium permanganate is 0.035 molar. The volume that it takes to make that titration successful is 17.48 milliliters. And from my previous page, the coefficient for the MnO4 is 1 mole. So then if I have this set up and then I solve for my Fe2 plus, my concentration of Fe2 plus is going to come out to be 0.3059 molar, which if we round that with significant figures is going to be 0.306 molar. Okay, so again, this is how I would probably solve a titration, but you can do the stoichiometry way that you see on the answer key as well. I am just not going to go over both of them. All right, for F, it says to deliver the 10 milliliter sample of the Fe2 plus solution in part E, the student has a choice of using one of the following pieces of glassware. You get a 25 milliliter burette, a graduated cylinder, a beaker, and a volumetric flask. So it says, explain why the 25 milliliter volumetric flask would be a poor choice for delivering the required volume. Well, it tells me I want 10 milliliters, and if you know how a volumetric flask works, a volumetric flask only gives you 25 milliliters. So I would discuss that. I would make a comment about, well, actually the answer key does a really good job of that. It says the volumetric flask is designed to contain only 25 milliliters. So I would just discuss that part there. I don't feel like I really need to work over that one. All right. For G, it says, in a separate experiment, a student is given a sample of powdered Fe that contains an inert impurity. The student uses a procedure to oxidize the Fe in the sample to Fe2O3. The student collects the following data. So you have the mass of the iron with this impurity, and then they heated it up, and then they produce this much of the Fe2O3. So it says to calculate the number of moles in Fe in the Fe2O3 produced. So there isn't an equation here, and it kind of maybe might freak you out a little bit, but what you need to remember is that if you look at Fe2O3 and you start with that from pure iron, you are going to need 2 Fe's to make that happen. So when I talk about my stoichiometry in this situation, it is just going to be a 2-to-1 mole ratio. So I have, based on my data, 7.531 grams of Fe2O3 to start off with that I produced in my situation or my particular experiment. Then what I want to do is I need to convert those grams into moles of Fe2O3. Got to find your molar mass. So 1 mole of Fe2O3 weighs 159.7 grams. You can do that math on your own. And then here is where the mole ratio is important. And again, since there's not an equation, you're probably going to have to just kind of understand that it takes 2 moles of Fe to make Fe2O3. Okay, so it's only asking me to find the moles of iron produced here. So if I go through and I do my work, I should end up with 0.09431 moles of Fe. Okay. For H then, it says calculate the percent by mass of iron in the original sample of powdered iron with the inert impurity. So the idea is that in theory, if all the iron is able to react and turn into iron oxide, this number of moles that I have here should end up being all the iron that's in there, and I can figure out how much iron is in there versus the impurity. So what I need to do first is I need to do 0.09431 moles of Fe. And then I need to convert those into grams of iron. So it's going to be 55.85 grams of iron for every mole of iron. And when you get the grams, it's 5.267 grams of Fe. So that's how many grams were in this original sample here. So I heated this original sample up. Then it made this many grams of the iron oxide, in theory, from all of the iron that was in there. And if I go back and kind of do the math, basically finish off my stoichiometry for part H, I end up with 5.267 grams of iron. Now it's asking me to find the percent by mass in the sample. So my original sample is going to be 6.724 grams. And what I will do is I will take my 5.267 grams of iron and divide them by the 6.724 grams of my sample, multiply by 100%, and I end up getting 78.33%. Okay? Hopefully that's a little bit more clear as to where that is coming from. All right. The last question on this FRQ says, if the oxidation of the Fe solid in the original sample was incomplete, so that some of the 7.531 grams of product was FeO instead of Fe2O3, what would the calculated mass percent, or would the calculated mass percent of Fe be higher, lower, or the same as the actual mass percent? This one I think is easy to understand what's going on, but challenging to answer correctly. So if you think about FeO, it is by mass 1 to 1. And what I mean by that is for every 1 iron, there is 1 oxygen's mass in there. In Fe2O3, there is 1 mass of iron for every 1.5 oxygens that are in there. So if you think about the percentages of iron, this FeO is going to have a higher percent iron than Fe2O3. And the reason it's going to have the lower percent iron for Fe2O3 is, again, because for every 1 of the irons, there's 1.5 oxygen. So there's just a higher proportion of the oxygen in the actual compound that we're trying to get. So what they're saying in the problem is that we thought all of this Fe2O3 was made, but in reality, the FeO may have made some of that. And what that's going to do is, the reality is that you have more Fe than you thought. Okay, so the actual lab conditions are that I have more iron than I anticipated. But my calculation, assuming that it was all Fe2O3, means that I think it has a lower percentage of Fe. So what's happening is, because I assume all of it is a product that has a lower percentage of iron, my calculated value is too low. My true value is high. But in this case, it is asking me about the calculated mass percent. So we would be talking about the calculated percentage would be lower because Fe2O3 has a lower iron to oxygen ratio, and therefore its mass would be lower. Hopefully this clears things up. If you have any questions, send me an email or we'll clear it up and meet.